Our investigation was conducted within the intercropping experiment, which aimed to investigate the underlying mechanisms of the effect of intercropping on crop productivity. Several studies have indicated that intercrop systems, or the use of a cover crop, can reduce weed pressure and improve the efficiency of integrated weed management. In either case, the evidence suggests that altering planned biodiversity of an agroecosystem can result in beneficial changes in certain aspects of associated biodiversity, such as weeds. Our experiment is based on the rationale that because intercropping increases diversity in the cropping system, there is an enhanced crop utilization of resources such as light, nutrients, and water. This practice demonstrates the potential to not only suppress weeds, but also to reduce herbicide use in agroecosystems, thus increasing system stability and sustainability. Ultimately, our objective was to evaluate the impact of biodiversity in space through intercropping and monocropping systems on weed populations. The experimental variables include species dynamics, richness and abundance, vegetative cover in space, total biomass, in addition to the height over time of a single tract weed.
Measurements were taken in one row within the intercrop experiment. Data was collected from 4 plots, each of different treatments. Treatments include corn monocrop, squash monocrop, bean monocrop, or intercrop containing corn, bean, and squash. At the center of each treatment, a 2-foot by 2-foot square was flagged to ensure that the quadrat was placed in the same area over the course of the experiment. Within the flagged squares, a single weed of the dominant taxa was flagged at the cotyledon state. The flagged dominant taxa's height was recorded in centimeters throughout the rest of the experiment. Data was collected on a bi-weekly basis. All weeds were identified using the UC A&R Weed ID monitoring cards. Once identified, the weeds were counted and recorded. Grasses were categorized into a single group, due to the difficulty of identifying the species of grass with accuracy. After identifying and recording the weeds present, canopy cover was taken using the Canopio smartphone application. At the end of the experiment, quadrats were again placed around the flags, and all above-ground vegetation was identified and removed. Once the above-ground biomass was taken from the field, its fresh weight was weighed in the headhouse. The biomass was then again weighed after being dried.
This graph illustrates that for each treatment, the number of grasses was substantially higher than the number of broadleaves. Out of the broadleaves, field bindweed was observed the most in each treatment. In addition, each monocrop treatment had a higher count of individual weeds than the control and intercrop treatments. This graph shows the observed species abundance in each of the treatments. We identified 5 different weed species in the intercrop plot, and as you can see, the intercrop plot had the lowest number of weed species compared to the 4 other treatments. There was a tie between 3 of the treatments for the highest weed species abundance. We observed 7 different species in each of those treatments, which were the control, the squash monocrop, and the bean monocrop.
This graph represents each weed species' contribution to the final total biomass per treatment. As seen in the graph, all treatments are dominated by grasses. In the crop treatments, common lamb's quarters has the greatest broadleaf biomass, but in the control plot, the greatest broadleaf biomass is contributed by wild radish. The corn monocrop has the lowest total biomass, while the bean monocrop has the highest total biomass. This graph outlines the growth of a targeted field bindweed in each treatment. As seen in the graph, the lowest growth rate was observed in the corn monocrop, while the highest growth rate is observed in the bean monocrop, followed closely by the intercrop experiment.
We have 4 main points of improvements for future cohorts. The first is to perform multiple repetitions for each cropping system, which would utilize multiple rows. You are not restricted to the row you initially planted. The second improvement would be perform germination modeling of resident weed species in a greenhouse setting in order to observe changing growth stages. The third improvement is bringing weed specialists out to the field on week 3. Once the weeds have established, they are more easily identifiable. The final improvement would be to consider the use of pre-emergent herbicides targeting grass species in order to easily monitor population dynamics of broadleaf weeds. This is not sustainable, nor is it an environmentally sound practice. All of the suggested improvements will add quality and data to the experiments. However, it will also add more time, work, and more data to be deconstructed and used.